In section 2.1, we learned that a set is a collection of elements with some common characteristic. Oftentimes, within a set, we can find subcategories or patterns within that set. We call those subsets. For example, in the set of all natural numbers, we can look at two subsets, the subset of even natural numbers and the subset of odd natural numbers. In section 2.2.1, we will learn about subsets and improper subsets. Note, recall from the last section that two sets are equal if they have exactly the same elements. Remember, equivalent sets have the same cardinal number, but equal sets have exactly the same elements. Keep that in mind as we go through this definition. Set A is a subset of set B, denoted A is a subset of B, if every element of A is also in B. So notice we have a new symbol to learn here. Recall from section 2.1, we learned this strange-looking E symbol. We read this as is an element of. That expressed set membership. Remember, if we slash that, it negates that phrase and we read it is not an element of. The new symbol that we're learning here expresses the relationship between sets. We read this one is a subset of. So we read that phrase, A is a subset of B, if every element in A is also an element of B. So if this symbol represents the subset relationship, what do you suppose happens when I slash that symbol? We're simply negating that phrase. This means A is not a subset of B. Now, we can make this a more stringent definition next. Set A is a proper subset of set B, denoted, we still read it, A is a subset of B, if A is a subset of B, think subcategory, and A is not equal to B. So if I compare these two symbols, the first symbol we learned has half of an equal sign on the bottom. So it's expressing the relationship between A and B in the fact that A is a subset of B, but it also allows for the possibility that those two sets are equal. However, this new symbol, the proper subset symbol, shows that every element in A is also in B, but it does not allow for the possibility that A is equal to B. So A is a smaller set than B with the proper subset symbol. Sometimes one symbol is correct and sometimes they can be used interchangeably. In example 1, we will determine if the proper subset symbol or the general subset symbol, or maybe both, may be used in the statement. So notice the first example has sets given in set builder notation. We read the first set as the set of all X such that X is a person living in Amarillo. The second set we would read the set of all X such that X is a person living in Texas. First of all, is the set of all people living in Amarillo equal to the set of all of the people living in Texas? No, this set is a smaller set than the set of all people living in Texas. So it would be appropriate to use the proper subset symbol. And that's the most specific expression of the relationship between those two sets. However, we could also use this symbol because it expresses that the set on the left is a subset of the set on the right, while allowing for the possibility but not requiring that the two sets are equal. So both symbols would be correct in example A. In example B, we also have sets given in set builder notation. We read the first set as the set of all X such that X is an element of the natural numbers and 1 is less than X is less than 10. Now, before we look at the other set, let's convert this to roster notation so we can identify exactly which elements belong to this set. Notice we're using strict inequalities. That means they do not allow for the possibility of equality. So 1 is not the smallest number in the set. 2 is going to be the smallest number in the set. And remember, we're only dealing with natural numbers, so we can exclude negative numbers and fractions and decimals. So we have elements 2, 3, 4, 5, 6, 7, 8. And we stop with 9 because the elements of this set have to be strictly less than 10, not equal to 10. So there we have the set in both set builder notation and roster notation. Looking at the set on the right, we read it the set of all y such that y is an element of the natural numbers and 1 is less than or equal to y is less than or equal to 10. Notice we've switched from strict inequalities, those without the equal sign, to inclusive inequalities, those that allow for the possibility of equality. If I write this set in roster notation, the first element in this case will be exactly 1, and then we will stop when we get to 10. Now we can decide which symbol will be appropriate. Notice that every element in the set on the left is also an element of the set on the right. So we are definitely dealing with subsets. And in particular, because the set on the left is smaller than the set on the right, the proper subset symbol would be appropriate. But it is also correct to use the general subset symbol because although it allows for the possibility of the equality of two sets, it does not require it. But keep in mind, the most specific expression of the relationship between those two sets in both of these examples is that proper subset symbol. Example 2. Determine if subset or not a subset should be used in the statement. So in this case, we're not concerned about proper subsets or general subsets. We're just concerned, is it a subset or not? Example A, the set on the left, we have elements 2, 19, and 11. Notice that set is given in roster notation, so we can see the elements of the set, and we could also observe the cardinal number of that set is 3 because it has 3 elements. The set on the right has elements 1, 2, and then an ellipsis. That means that pattern continues until we get to 15. So it looks like we're dealing with the numbers between and including 1 to 15. Now, is every element of the set on the left also an element of the set on the right? Actually, no, right? 19 belongs to the set on the left, but it does not belong to the set on the right. So because every element in the set on the left is not also an element on the set on the right, we would have to use the not subset symbol. Example B, the set of all x such that x is an element of the natural numbers and x is greater than or equal to 5. Now, to make it simpler, let's go ahead and translate this into roster notation. That is, let's list the individual elements of this set. We're dealing with natural numbers or counting numbers, and we're looking at numbers greater than or equal to 5. So we would start with 5, and then we would count our way up, and notice this would be an infinite set. So we can express that with the ... We read the set on the right as the set of all y, such that y is an element of the natural numbers, and 1 is less than y is less than 10. Now, let's go ahead and translate this one also into roster notation. We are dealing with counting numbers or natural numbers, and notice we have strict inequalities. Can you figure out the first element of this set? That would be 2, and then we would continue counting, and we would stop at 9 because the elements of this set have to be strictly less than 10. Now let's see if we can determine the relationship between these two sets. Is every element of the set on the left also an element of the set on the right? Well, the ones I have written certainly belong to both sets. However, this ... indicates that we keep counting even beyond 9. So the set on the left is bigger than the set on the right, so we would have to use the not subset symbol. So in this section, we learned about subsets, which is a subcategory of a given set. A proper subset is smaller than the original set, and you've got a couple of new symbols to learn: the general subset symbol, the proper subset symbol, and the negation of those two. You can add those to your list of symbols that you're learning for this chapter.